Okay. Um, Keep in mind that I am using a new microphone, and I think I can't figure out quite how to do this. So I'm redoing the first half of this, and then I'm connecting it to the back end of this thing. Who knows if this is going to work? But here, this picture I'm showing of the storm going on right now, just outside. Craziness! I can't believe it's snowing as hard as it is. All right. So recall, crew, that we are looking at something called standard enthalpy of formation. And what I have written here in black is what I had you write down in class today. And it's the way that we solve these problems using this special equation to do this. And the best thing to learn how to do this is to simply get into a problem itself. So here's the kind of problem that you'd be faced with. Let me just read it to you. Carbon monoxide burns to form carbon dioxide. Write a balanced equation to show the reaction and provide the enthalpy change of the reaction. Now, what's important for you here, and actually let me go ahead and make this disappear for a moment. This is confusing. When you look at this reaction here, obviously it's not balanced. And so the first thing you need to do is go ahead and do the balancing, which is what I had here moments ago. But the problem is when you go to balance this, you can see here, it's not really a problem, but I want you to at least note it, that this is not enthalpy of formation for carbon dioxide. All right, that's an important thing because the enthalpy of formation for carbon dioxide would just simply be carbon plus oxygen yields carbon dioxide. So don't get confused by that. This is just a regular old chemical reaction that's going on. And what we're going to do is use the enthalpy of formations to figure out the enthalpy change for this entire reaction, which is the combustion of carbon dioxide. And to do this, we're going to use that equation. And I want you to note a couple things here that I've put together. Number one, if you go back and look at the balanced equation, you'll note that there's 2 carbon dioxides over here and 2 carbon monoxides over here in the reactants. And if this right here represents my products, this is my carbon dioxide, I have to make sure that that 2 is represented in this equation because I'm going to have 2 carbon dioxides. And if I consult my table that I gave you guys today, and it's in your Dropbox, you would find that a single carbon dioxide, its enthalpy of formation, standard enthalpy of formation, would be negative 393.5. And if I do the same thing but with my products, you can see here that I have, for my reactants, I have carbon monoxide and I have oxygen. And if you look up carbon monoxide on the table of enthalpy, standard enthalpies of formation, you would find that that would have a value of negative 110.5 kilojoules. But since I have to have 2 of them, it's essential that I have the 2 here in front of the parentheses. And then another thing that's really wacky is if you look right here, I have a 0 for the oxygen. Well, that's totally fine because you should know that elements that are in their standard state are always going to have an enthalpy of formation of 0 because they simply exist. It doesn't take energy for them to come into play because they exist out there in the real world. All right, so we have oxygen out there, we have carbon out there, we have hydrogen out there. But of course, it has to be in their standard state. So in fact, instead of it being just plain oxygen, an atom of oxygen, that's not how you find oxygen in the standard state. You would find it as O2. So all the Honkelbriefs in their standard state are diatomic molecules. Don't forget that. All right, so anyway, we have 0 here representing our oxygen. We have our 2 carbon monoxides here. We have our 2 carbon dioxides here as our products. When you sum it all together, it gives you the enthalpy change for this reaction, the standard enthalpy change for this reaction of negative 566 kilojoules. Now, this would be a remarkably simple problem. They're never quite right. So let's look at something else. Okay, so here's the question that I'm going to underline here in brown, which is to calculate the standard enthalpy of formation for solid MgOH2. So how do you go about this problem? And I give you those three reactions above to help you do this. This seems kind of tricky. Well, the first thing I want to point out to you is that you can see we have MgOH2 in a reaction here. Now, this reaction is showing the decomposition of MgOH2, but it is a reaction nonetheless that has MgOH2 in it, and that's our goal. Is we want to find how to calculate the standard enthalpy formation for solid MgOH2. Well, don't forget now that our reaction, or I'm sorry, the equation we use is that the enthalpy, oops, I meant point. The enthalpy change for a reaction overall is going to be the sum of the products of the enthalpy of formation of the products minus the sum of the enthalpy of formation for the reactants. Okay. Okay, so follow along what we're going to do here now. We are going to focus in on the fact that this reaction has it absorbs 37.1 kilojoules of energy. So let's just focus entirely on this reaction. I'm going to put a line underneath it to help us figure out what the standard enthalpy of formation for magnesium hydroxide is. Now, it gets a little tricky here, but you'll figure it out soon enough. So I'm going to have my equation. Actually, let me bring that equation back over here so you can see it. Let me select this thing up. Oh boy, struggling here. I put it too close to the edge. Okay, so let me copy this, scooch over here, paste it. All right, so my enthalpy change for any reaction, all right, I'm going to go ahead and I'm going to use this up here. So we're going to take 37.1 kilojoules. And that's going to equal, I have to focus in on the one that I just underlined in purple here. That's going to equal the enthalpy change of the products. And of course, the products in this case are MgO and water. Okay, you can see that right up here. And the reactant, there's only one reactant here, is going to be my MgOH2. And don't forget, that's what we're trying to go for here. I'm trying to calculate the standard enthalpy of formation for the MgOH2. So this is my question mark right here. Now, if you look at the other parts of this equation, these things are tremendously helpful because you can see here in this first equation, it looks like I have a standard enthalpy of formation for MgO, which I need. And it looks like we have a standard enthalpy of formation for water, which I also need. But don't forget, what do you need to do to these reactions in order to get them to be truly standard enthalpy of formations? It has to be a 1 here. So we have to change those things. In other words, now, I'm going to convert this first equation here by dividing it all through by 2. I'm going to make it 1 mg plus 1/2 O2 yields 1, oops, I don't need to do that, MgO. And of course, since I divided all that by 2, I have to divide my standard enthalpy there by 2 as well. And when I do that, instead of having 1203.6 kilojoules, I'm now only going to have negative 601.8 kilojoules that evolve from that process, right? And if you look at this, indeed, this is a standard enthalpy of formation because I'm starting with the elemental bits, magnesium and oxygen, to make my magnesium oxide. So in fact, I can go ahead now and convert this into a standard enthalpy of formation by adding that very important F down there. Let's do the same thing now, but do it for the water. So I'm going to take my water, I'm going to divide that whole thing through by 2 as well, so that I can leave me with 1 mole of water. So that'll be H2 plus, again, 1/2 O2 yields a single H2O. And my standard enthalpy change for that has to be half of the 571.7 kilojoules. And when you calculate that, when you divide that by 2, it becomes negative 285.85 kilojoules. And you can check that with the diagram that I gave you, or the table that I gave you guys earlier, to see that that is indeed the standard enthalpy of formation for water. And also you can confirm this because the water is made up of just these elements, hydrogen and oxygen. Now this becomes super handy, right? Because now I'm going to take this value that I just created here, hold on, copy this, okay, right here, and I'm going to place it right above my magnesium oxide here. Let me move some things around, hold on. Okay, I hope you see what I just did there moments ago. I simply moved these values that I just created into their spots right above what it is that they represent. So MgOs, standard enthalpy of formation, water's standard enthalpy of formation, and I'm going to sum those two things together, all right, just like we show right here. Yeah, it's a sum of all the products. And I'm going to subtract away the standard enthalpy of formation for my MgO, which is what I'm looking for. That's my big question mark, and that's what I'm aiming towards. All right, so then you just throw this into the calculator. You see here I've just sort of simplified it all by pulling it all together down there. And if you solve for that question mark, you are indeed going to get a value of negative 924.75 kilojoules. And don't forget, the question mark is indeed the standard enthalpy of formation for our MgOH2. There you have it. Now, the question you might have is, wait a second, if we are looking for the standard enthalpy of formation for magnesium hydroxide, why not simply take this reaction that we have here and turn it around? Because that would be, instead of the decomposition, that would be the formation of MgOH2. Well, the reason that's the case is that that's not the formation. That's not the reaction for the formation of MgOH2. The reaction for the formation of MgOH2, in fact, is this, which is very different. It's, oops, sorry about that, Mg plus O2 plus H2 gas leads to the formation of MgOH2. All right, and that's the proper enthalpy of formation for this dude. All right, so compare this reaction that we have right there to this reaction that we have right here, and I think you can see that those are very different things. Even if I were to flip this around, right, and had MgO plus H2O as my reactants to make MgOH2, that would not be a standard, it would not be enthalpy of formation that we have going on there. I know this is all difficult. I promise you that it'll be clearer as you begin to put things together, and life will be much easier. Okay, goodbye.